Dear audience, I am Dr. B.Sc Associate Professor, Department of Electronics and Communication Engineering, SR University, Warangal, Telangana, India. Today's session will be described, first of all, the summing amplifier, and that is non-inverting, because in our last class we have completed inverting summing amplifier. So today's session will start with non-inverting summing amplifier. Non-inverting non-inverting summing amplifier using op-amp. So let us draw the circuit diagram first, then only we can explain the working mechanism and the output voltage waveform, output voltage expressions. So that is important. First we will draw the circuit diagram. So this is minus terminal, this is plus terminal. So this one, this is feedback resistor RF, this is input resistor R, and this is must be grounded. Now because of the non-inverting amplifier, so all the inputs should be connected at non-inverting terminal only. So this is the first source, this is the second source, and this is the third source we will connect and join together. So this is V1, this is V2, and this is V3. And correspondingly we are writing the resistances R1, this is R2, this is R3, and this is connected to the non-inverting terminal. Let us consider this point is A, this point is A, this node is A, and this voltage as per the virtual ground concept, this point, if this point voltage is VA, suppose this node voltage is VA, and this point voltage should be VA because of the virtual ground concept. Now suppose this is the output voltage V0. So we have to find out V0. What is we need to find out? We have to find out V0. So what is V0? That we have to find out. So let us start. As I mentioned, the potential at this point is VA. So now we will find out the current component, this path, and this path. Suppose this current is I1, this current is I2, and this current is I3, say for example. So what is I1? So in this point, it all currents I1 plus I2 plus I3 at node A should be 0. At node A, that should be 0 as per KCL. As per KCL, as you know. Now we know what is I1. So this voltage is VA. So V1 minus VA by R1. So that is I1. V1 minus VA by R1. Similarly, plus I2 should be V2 minus VA divided by R2 plus V3 minus VA by R3, and that is nothing but 0. So this is the most vital expressions. Okay. So now from this expression, what we will find out? We will find out VA. What is VA? So now VA is equal to, we may take all VA commons, V1 by R1 plus V2 by R2 plus V3 by R3, and minus V1 by R1 minus V2 by R2 minus VA by R3. So what will happen? So V1 by R1 plus V2 by R2 plus V3 by R3 one side. Other side, it should be minus VA if we take common. So 1 by R1 plus 1 by R2 plus 1 by R3, that is equal to 0. Now, so VA 1 by R1 plus 1 by R2 plus 1 by R3, that is equal to V1 by R1 plus V2 by R2 plus V3 by R3. Now what is VA? So from there we can easily write what is VA. VA is equal to this by this. So V1 by R1 plus V2 by R2 and plus V3 by R3 divided by 1 by R1 plus 1 by R2 plus 1 by R3. So that is the expression. So we may say that this is expression number 1 for the sake of simplicity. Now we know that the op-amp having two resistors RF, and this is RF and R, and this point voltage is VA. So from that expressions we can find out the output voltage for non-inverting amplifier. So the output voltage for a non-inverting op-amp, that is V0, it should be 1 plus RF by R1. R1 means here R into this node voltage. This node voltage is how much? VA. That one voltage VA. So into VA. Now we know what is VA. So this is the VA. Now what should be V0? V0 is equal to 1 plus RF by R as it is into VA. What is VA? VA is equal to this much expression. So that I will put here. So I am taking different color to make you understand. V1 by R1 plus V2 by R2 plus V3 by R3 divided by 1 by R1 plus 1 by R2 plus 1 by R3. Okay, so this one. Now we'll take some assumptions. Let, now at this stage, R1 is equal to R2 is equal to R3 is equal to, we are telling that R. And R is equal to, I am telling RF by 2, half of RF. Then what will happen? So all will be R1, R2, R3 and R1, R2, R3. All are R. We can say that. So first we will put all R. Then R is equal to RF by 2. Finally we will put. So what should be the V0? So V0 is equal to 1 plus RF by R. Okay. This is okay. Now V1 by R plus V2 by R plus V3 by R divided by 1 by R plus 1 by R plus 1 by R as per the expression here, because all R1, R2, R3 is equal to R. So what will happen? 1 plus RF by R, and here 1 by R we can take common, and V1 plus V2 plus V3, and here 3 by R. 1 by R, 1 by R, V by R. So now what will happen? So this R and this R will cancel out. Okay. So now we will put R is equal to RF by 2. As I mentioned, R is equal to RF by 2. So 1 plus RF, then R by RF by 2. So it will go outside, and V1 plus V2 plus V3 divided by 3, because R cancel out. So now what happened? R cancel out. 2 plus 1, 3. So 3 into V1 plus V2 plus V3 divided by 3. So now ultimately what happens? This 3 cancel out. This 3 and 3 cancel out. Ultimately what we are getting? V1 plus V2 plus V3. So V0 is equal to, ultimately what we get is that V0, that is the output voltage, is nothing but V1 plus V2 plus V3. So that is the non-inverting summing amplifier. At the output we are getting summation of all the inputs. So here V0 is equal to, what we get it, that what is now? That is, we are getting V0 is equal to V1 plus V2 plus V3. So that is the final expression. So this is all about our non-inverting summing amplifier. Okay, hope you people understand. Now we will go for integrator circuit. Now we will go for integrator circuit. That is very much interesting, and that is most important also, because this integrator circuit is nothing but a low pass filter. So whenever we go for designing any communication circuit, basically in the receiver stations, we are going to use this integrator circuit because it is used as low pass filter. So now we'll go for integrator circuit. What is that? Integrator circuit using op-amp. So let us draw the circuit first. So this is op-amp as usual, minus plus. This is output. This is input resistance. Here instead of resistor we will use one capacitor C, and this is R, and this is input voltage, that is Vi, and this is grounded in general. So now this current is I1, okay, and this current IF or IC because of the capacitor is there. So now we will find out the expression for this integrator circuit. Okay. So now we know that U is equal to CV. So dq dt is equal to C into dV dt. So I is equal to C into dV dt because dq dt is equal to I. That I am telling you, just a general expression. Now here this is also 0, this is 0, so this is also 0 volt because of the virtual ground. So current I1 must be is Vi by R. Now this IC, what will the IC current? Because if it is IC, from here if we write IC is equal to C into dV0 dt. Why dV0 dt? V should be V0 because this voltage is V0. This capacitor getting the output voltage V0. So that's why it should be current I is equal to C into dV0 dt. So that is I or IC. Okay, this IC, or that is you can say IF, that is equal to C into dV0 dt. Now what is the current component here? Here I1 plus IC, that is equal to 0 because all the current component meeting in this point is 0. So I1 is equal to IC. What is I1? I1 we get Vi by R. What is IC? C into dV0 dt. So now in the next page I will write, and this is must be minus sign here. I1 is equal to minus IC. So what is I1? Vi by R is equal to minus C into dV0 dt. Now we have to find out V0. So dV0 dt is equal to minus 1 by CR Vi. Now dV0 is equal to minus 1 by CR Vi dt. Now take integration both sides. So dV0 integration 0 to t minus 1 by CR Vi dt. So ultimately dV0 means it is V0. So minus 1 by CR, it's a constant, so it will coming out side, and Vi dt. So now this is the final expression for the integrator circuit, and this is called scaling factor. Scaling factor is a constant value. Scaling factor. Okay. So V0, or rather we can say that V0t in this one, and here we can say that V0 0, the initial value. So this is the initial output. We can say that this is initial output when t is equal to 0. So this is the final expression for an integrator circuit. Now we will go for differentiator circuit. We will go for differentiator circuit. So I am giving the basic circuit diagram. Okay, so I am giving only the basic circuit diagrams. And later we will go for some numericals. So after finishing this theory, I shall go for some numerical calculations. So differentiator. Differentiator circuit using op-amp, because all are op-amp applications. So differentiator using. So now we'll make a circuit first. So that is most important. So here the integrator and differentiator, once I draw the circuit, you can understand the replacement of C and R. So first draw the circuit. This is minus, this is plus. Here the input capacitor we will connect. Here resistor will be there. This is V0. Okay, and this is grounded. Or you can hear one resistor also. So this is Vi. This is C. This is Ra. So now we may think this is IF current. Okay, feedback path. So IF. And this is also ground potential due to virtual ground, and I will thinking this is IC current. Now again here, as per KCL at this node A, IC plus IF is equal to 0. So from there, IC is equal to minus IF. Now what is IF? IF is nothing but V0 by RF. What is IC? IC is as per the previous expression, Q into C VI dt, because here V is equal to VI. So C VI dt, Q C VI dt. So C dVi dt. So C in Q, So current is equal to, or collector current is equal to C into dVi dt. So this is the collector current. Now we'll put here the current component. What is IC? C into dVi dt. And what is IF? IF is equal to this one. So V0 minus is almost there, V0 by RF. So from that expression we may write V0 is equal to minus C into RF dVi dt. So that we get the expression. What we get? So ultimately that is V0 is equal to minus C into RF dVi dt. So from that expression it is very clear that the input voltage is differentiated and we are getting the output. This is also scaling factor. So that is called differentiator, because input voltage is differentiated. In the integrator circuit, what happens? The input voltage is differentiated and we are getting the output voltage. Here input voltage is differentiated, so that's why it is called differentiator. So this is all about your integrator circuit and the differentiator circuit. But if we think for the practical differentiator circuit, then we may use some capacitor in the feedback path. Okay, some like this minus and this is plus. Here one capacitor is there, one resistor is there. So sometimes we are using here one capacitor, and this is V0 and this is grounded. Sometimes here one resistor also we connect, and this voltage will be there. So the VI, this is R, this is C, or we may say the C1, and that is CF, and this is RF. So here we may consider this is ZF, means the impedance. This is a complete, that is actually practical differentiator. Practical differentiator. So this is practical differentiator. So likewise, we may think about the practical integrator circuit also. So in that case, what we will do is that one resistor we will use in the path, in the feedback path. So in the feedback path, there we may use one resistor circuit. So practical or lossy integrator. Practical or lossy integrator. What we'll do? We'll use one resistor. This is minus, this is plus, this is grounded. Here one input resistor is there. This is Vi. This is R1. So here what we have done in the normal integrator C. Here one resistor we will use, that is V0. So that is RF. So this is the practical one. And here we will find out the gain. Gain of this circuit is V0 by Vi mod. So that will give you RF by R1 divided by square root of 1 plus omega RF CF whole square. And from that we can find out the frequency of operation, that is FA is equal to 1 by twice phi RF CF. So that is most important in the numerical in the exam. So this numerical solving this expression is useful. So FA is equal to 1 by twice phi RF CF. Similarly, in the case of differentiator, we also use some frequency of operation. In that case, the frequency of operation is 1 by twice phi RF CF. There also. What is that? There also, FB is equal to 1 by twice pi R1 C1. So R1 and C1. This is or RFCF. Here RFCF is there. So R1 C1. So this is R1. This is R1, this is C1. So R1 C1. So this is R1 C1. In this way frequency comes. So this is useful for differentiator. 1 by twice phi R1 C1. Which one R1? This is R1, this is C1. In the case of integrator, this is 1 by RF CF, this is RF, this is CF, this is CF. So RF CF. So this is all about integrator, differentiator, and the adder circuit with non-inverting summing amplifier. So these are most important. Now we'll solve few numericals. In the next video, we will only describe the numericals. So now, as we got some expressions, FA is equal to 1 by twice phi RF and C1, that is for differentiator. Now suppose we get a differentiator input signal with F max, the maximum frequency usually is 100 Hz, and we have applied one sine wave input with 1 volt peak at 100 Hz frequency applied to the input to the differentiator. And the question is design an op-amp differentiator. Design an op-amp differentiator. This is the question. Say for example, one question. Whatever given, the maximum frequency is given 100 Hz, and we are applying a sine wave. Amplitude is 1 volt peak, and frequency was 100 Hz. Now we know the formula. What is FA or F max in this case? That is equal to 100 Hz, and that is equal to 1 by twice phi RF into C1. Here C1 is equal to 0.1 microfarad. Okay. We are assuming let C1 is equal to 0.1 microfarad. So what is RF now? What is RF from this expression? So 100 will come here. Twice pi. This 100 comes there. If this come here, this will come here. 1 by 100 into C1 how much? 0.1 microfarad. Okay, so 0 microfarad means 0.1 into 10 to the power minus 6 farad. So if you calculate it, it will come as 15.9 kilo ohms. So RF we get 15.9. So we got the feedback resistors. So we got C1 and RF and input voltage and frequency. So this is now this differentiator is formed. For differentiator, what we need? The feedback resistor, RF, input capacitor C1. Okay, we got all the things. So this is verified. So this is all about the numerical one. So we may go for one more numerical. Very simple, I am asking. Suppose an inverting amplifier has R1 input resistance. How much? 20 kilo ohms. And what is RF? RF is given 100 kilo ohms. Question is find the gain. Find the gain and the input current. For an input voltage. Input voltage is given. Suppose input voltage of 1 volt. So Vi is equal to 1 volt given. RF is 100 kilo ohms given. R1 is equal to 20 kilo ohms given. All are given. So we know that voltage gain V0 for an inverting amplifier. What is inverting amplifier voltage gain? V0 by Vi is equal to minus Rf by R1. So minus Rf is how much? 100 kilo ohms by 20 kilo ohms R1. So minus 5. So gain is minus 5. So gain, that is V0 by Vi, that is equal to minus 5. Now what is input current? Input current is nothing but the input voltage by input resistance. So input voltage how much? 1 volt. Input resistance how much? 20 kilo ohms. So kilo ohms is there, so it should be 0.05 milliampere because this kilo ohm. So this is the case. So whenever we have a numerical, we have to understand what are the given parameters. Here given parameter R1 is 20 kilo ohms, RF is 100 kilo ohms, and input voltage is 1 volt given. So that then you write all the given parameters and check what you have to find out, because inverting amplifier is nothing but is something like that. So this is grounded, here one resistance is there, here also one resistance is there, and this is output voltage, and this is Vi. So Vi 1 volt is given, R1 is equal to 20 kilo ohms given, and this is 100 kilo ohms given, that is RF. So it is easily we can find out, because V0 is equal to minus Rf by R1. This is the formula into Vi. But V0 by Vi is gain, and that is equal to minus Rf by R1. So Rf is given, R1 is given, so gain automatically find out. And here input current, that is II. So current is flowing from this to this direction to this direction. This is 0 potential, 0 volt. So Vi by R1 is nothing but the input current I1. So V1 is 1 volt, R1 is 20 kilo ohms. So current will be calculated. So now this is all about our summing amplifier in non-inverting case, and integrator circuit, differentiator circuit, and 2 more numericals we have done here. So this is all about our today's session. In the next class we will definitely, whole video will come with more numerical, and those will be helpful for semester exam as well as some competitive exam. Even it will give you good idea to solve the numericals while you go for GATE exam. So my dear learners, students, keep in touch with me and follow all the videos, and if you like, don't forget to subscribe and like and share to your friends, those genuinely need these videos. So thank you for today's sessions, and we'll meet very soon with numericals, exciting numericals with next video. So thank you.